Hello friends, I welcome you in lecture number 32 on hypothesis testing. In this lecture, we will discuss one question on chi-square goodness of fit test. This question was asked in GTU Winter 2019 exam. The question is, a die is thrown 276 times and the results of these throws are given below. Number appeared on the die. We know that there are 6 possibilities, that either 1 turn up, 2 turn up, 3, 4, 5 or 6 turn up. So these are the numbers appeared on the dice. When we are throwing a dice, there are 6 possibilities, that either 1 occurs, 2 occurs, 3, 4, 5 or 6 occurs. And here they are throwing a dice 276 times. So they have given these frequencies for each number. If they are throwing a dice 276 times, then the number 1 appears 40 times, number 2 is appearing 32 times, and similarly they have given frequency for each of these numbers from 1 to 6. So this total must be equal to 276. And here they have asked to check or test whether the die is biased or not. We know that a die or dice is not biased if there are equal chances for each of these numbers to turn up. That is, probability is equal for 1, 2, 3, 4, 5 or 6 to turn up whenever we are throwing a dice. So in statistical language, we can say that if we are throwing a dice, then there are total 6 possibilities, and probability that x equal to 1 occurs is 1 by 6, and this must be same for each of the numbers if our die is unbiased or if it is not biased. So there are equal chances of occurrence for each number when we are throwing a dice. So we will assume that our die is not biased or unbiased, so that we can use these theoretical probabilities for each of the numbers, and using this theoretical probability we will find out the expected frequency for each number to turn up, and then we will compare these observed frequencies with those expected frequencies, and for that we will use chi-square distribution. And we are familiar with the formula for test statistic for chi-square goodness of fit test. It is given by sigma observed minus expected and the square of this difference divided by expected frequency. And here we can see there are 6 possible categories. There are 6 possibilities when we are throwing a dice, that either 1 occurs, 2 occurs or up to 6. There are 6 possibilities. So there are 6 categories. So we will consider small k equal to 6, which is number of categories or number of cells or number of groups for this goodness of fit test. And here they have given observed frequencies for each number on the dice, and if we assume that die is not biased or die is unbiased, and if that assumption is true, then theory says that the probability for each number to turn up must be same, and that is equal to 1 by 6. And there are total 276 throws in this sample. So to find out expected frequency, we will multiply each of these probabilities by 276, and here all the probabilities are equal. So if we multiply this 276 by 1 by 6, then we will obtain 46 expected frequency for each number from 1 to 6. So this 46 will remain same. We will consider null hypothesis H0 as that die is unbiased, and if we assume that this null hypothesis is correct, then probability for each number to turn up is 1 by 6, and there are total 276 throws of a dice. Therefore expected frequency will be equal to 276 times this probability, that is 46. So this 46 will be the expected frequency for each of these numbers from 1 to 6. So then we will find out value of this test statistic, and here they have not given level of significance. So we will consider level of significance as 5% or 0.05%. The number of degrees of freedom will be equal to k minus p minus 1, and here k is 6, and we are not estimating any parameter of the population using sample data, so small p will be 0. Therefore degrees of freedom will be equal to 5. So we will find out critical value at 0.05 level of significance and 5 degrees of freedom, and then we will compare this calculated value of test statistic with this critical value, and then we will take the decision. So this is very simple question. Whenever you have this type of example on throwing of a dice, and if they ask you to test whether the dice is biased or unbiased, then you should apply chi-square goodness of fit test, and here you can find out expected frequencies easily. There must be equal chance of occurrence for each of these numbers on the dice, and for that you have to divide total number of throws, that is 276 here, by 6 possible numbers, and you will have expected frequency 46 for each of these numbers. So if we have all the expected frequencies are equal for each of these numbers, then we can say that dice is unbiased. Or because we are assuming that null hypothesis is correct, that is die is unbiased, therefore if we assume that that is correct, then we find out expected frequency for each of the numbers simply by dividing 276 by 6, and we obtain 46 expected frequency for each of these numbers. So these are the frequencies if null hypothesis is correct, and we have these observed frequencies. They are considering 276 throws of a dice, and they obtain these observed frequencies. So we will calculate this test statistic using observed and expected frequencies, and then we will compare calculated value of test statistic with critical value using chi-square table. So this is the main idea for answering this question. I have written all these things systematically here. First, I have mentioned that the die is unbiased if there is equal chance for each number to turn up when the die is thrown. That is probability that capital X equal to small x is 1 by 6. Here we can consider capital X as a random variable which shows the number on a die. So possible values of capital X are 1, 2, 3, 4, 5 and 6. So we will consider capital X as random variable under consideration for this problem, and we have to find out the expected frequencies using these probabilities. So first we write down null hypothesis, that die is unbiased. Alternative hypothesis is opposite statement to the null hypothesis, that is the die is not unbiased. Or you can write null hypothesis as suppose the die is not biased, and here you can write that die is biased. Okay, both are equivalent statements, and we will select a level of significance as 5%, that is 0.05. If null hypothesis is correct, that is if die is unbiased, then probability is same for each of the number to turn up, that is 1 by 6. And here I have prepared the table for observed and expected frequencies. These are the values of random variable capital X, which is number on a die, and possible values of X are 1, 2, 3, 4, 5 and 6. These are the observed frequencies from the question. They have given this sample data after throwing a dice 276 times. So here this total must be equal to 276. This is the expected probability for each of the numbers. There are same probabilities to turn up, that is 1 by 6. And expected frequency is obtained by multiplying these expected probabilities by total number of throws, that is 276. And there are equal numbers for expected frequency for each of these numbers. So 1 appears 46 times, 2 appears 46 times and so on. 6 appears 46 times and this must be equal to 276. We have to check that whether all the expected frequencies are at least 5 or greater than or equal to 5 to apply chi-square goodness of fit test, and here all the frequencies are obviously greater than 5. And then we have calculated the test statistic for goodness of fit test, sigma observed minus expected frequency whole square divided by E. So here we are considering 40 minus 46 whole square divided by 46. This is for number 1 or first category. Then 32 minus 46 whole square divided by 46. Similarly 29 minus 46 whole square divided by 46. Then 59 minus 46 whole square divided by 46. Next one is 57 minus 46 whole square divided by 46. And last one is 59 minus 46 whole square divided by 46. And using scientific calculator up to 4 decimal places, I obtain these real numbers for each of these terms up to 4 decimal places. And if I sum all these values, I obtain value of test statistic as 21.3043. Now number of degrees of freedom are given by this formula for this test, k minus p minus 1. K is the number of categories or groups or cells, and here we have 1, 2, 3, 4, 5 and 6 categories. So we take k equal to 6. Small p is the number of parameters of the hypothesized population which are estimated by sample data. Here we are not estimating any parameter using sample data. Therefore we consider small p equal to 0, and therefore we have 5 degrees of freedom. Level of significance is alpha equal to 0.05, and we know that chi-square goodness of fit test is always right-tailed. Therefore we have to consider 0.05 area in the right tail. So let me roughly sketch this chi-square curve, probability density curve for chi-square. And we know that it is always taking non-negative values. Values of chi-square are on the horizontal axis. We consider area of 0.05 in right tail, because this test is always right tail test, and this point is denoted by chi-square suffix 0.05 and with 5 degrees of freedom. And in the chi-square table I have to search for this critical value. So I am going for this table. Here I have to first search for 0.05 level of significance. All these values are for the level of significance or areas to the right of that critical value. Here they have mentioned area to the right of critical value. and these are the degrees of freedom. We are in search of 5 degrees of freedom and this level of significance. So we consider intersection of this row and column corresponding to 0.05, and we find out this point at the intersection, and this point is our required critical value, and it is 11.071. The value of chi-square at alpha equal to 0.05 level of significance and 5 degrees of freedom is 11.071. So this number is 11.071 using chi-square table, and you can see this calculated value of test statistic is 21.3043. So it is obviously to the right side of this value 11. Suppose somewhere here, suppose this value is calculated value of test statistic, and we know that the region to the right side of this critical value is rejection region, and if calculated value of test statistic is in rejection region, then we reject the null hypothesis. I have written all these things here again. Alpha is 0.05. Using table we find this critical value as 11.071, and because calculated value of test statistic is greater than 11.07, calculated value of test statistic is say somewhere here, chi-square is 21.3043. This number is 11.071. So chi-square calculated value of test statistic is greater than critical value. Therefore, we reject the null hypothesis. And the null hypothesis is that the die is unbiased, and we are rejecting that statement. So we can say that there is not enough evidence in the sample data to suggest that the die is unbiased, because we are rejecting the null hypothesis, and null hypothesis is that the die is unbiased. So this is very simple question. You have to understand that here they have given these observed frequencies, and you can see there are different chances for each number to turn up. But if dice is unbiased, then there must be equal chances for each number to turn up. These are the observed data, and we can see there are differences here, and from this we can have the idea that the chances are that the dice is biased. So what we are doing, we are considering equal chances for each number to turn up, and for that we divide total number of throws by these 6 possibilities, and we obtain 46, and then we apply this chi-square test statistic to test whether the die is biased or not with 5% level of significance. So they have asked this question in GTU Winter 2019 exam and also in 2022 exam, and the question is very easy. All you have to remember is this formula for chi-square test statistic, and rest of the things you can easily do with clear concept of chi-square distribution. So this is all about this session. I hope you like it. Thanks for